So welcome to this lecture. Today we will discuss about condition of convergence and stability in discretized solution. So first let me discuss with this discretized solution. What is discretized solutions? As you can see that if there is an equation like this, so plus suppose a t x and 0. So this is one of the partial differential equation. And when we try to find the solution of this equation, in case of differential equation, solving of differential equation, what we try to find is with respect to its independent variable x and also t. This temperature T, this is actually the temperature, x is the space, and t is the time. So suppose I want to know if this is the rectangular plate, right, and I have to know what is the temperature at these points or inside the plate with the help of the temperature at the edge. Suppose we know what is the temperature at the edge. So this is 70, this is 90, this is 80, this is 120 degrees centigrade. I know the temperature of all these areas, as you can see. But now I want to know what is the temperature at the inside of this metal plate. Now to know this, you have to solve the differential equation which represent the heat conduction through the metal plate. And if you can solve that equation, then you can know that what is the temperature at this point at a certain time. Suppose if I say at t is equal to 0, what is the temperature at any point I plus 1 and I minus 1? What is the temperature? Now, what is this I plus 1? If I divide this metal plate into grids of uniform dimension, right, then each of the grid point is your I. That means if this is the first grid point and this is the 0th grid point, then this will be 2, second grid point, third grid point, fourth grid point, fifth grid point, then this one will be 6th, 7th, 8th, 9th, 10th, and so on. And remember, this each of the grid is uniform dimension. That means this and this is same. And if I represent this axis as x and this axis as y, and each of this distance, if we represent this as del x and this represent as del y, then all this grid has a side del x and del y which is equal, right? And if I say this point is I, Then with respect to this point will be I plus 1 and this point will be I minus 1. Now I want to know the value of temperature T at this point or on this point at T is equal to 0. So we have to solve the heat transfer equation and need to find the solution to find the temperature at I plus 1 and I minus 1. The Taylor series expansion of that equation will give you the value at T at I plus 1 and T at T on I minus 1 at time T is equal to 0. Generally we use the central difference of the partial differential equation. Now the same partial differential equation can be solved by the simple ordinary differential equation. In that case, what happens is we generally try to find the temperature of heat or the inside temperature where the domain, if this is your domain, right, bounded by these sides, which temperatures are known, these sides or edges, which temperatures are known, then the differential equation will give the inside temperature of the plate, but not on each point of the inside of the plate. Okay. So what it will give is it will give the temperature at the entire space within this within the metal plate. If this is the metal plate, then the solution to the partial differential equation by differential solution method will give you the temperature inside the metal plate. And it will find it with the help of the temperature at the outside. Okay. If I know the Tx dash, Tx, Ty and Ty dash, differential equation solution will give the temperature at this place, this inside space. But this will be can be erroneous because suppose it is giving T, but this T can be different here, can be different here, can be different here, because we know the temperature here, we know that the heat is being applied in this side. So while conducting at time T is equal to 0, it can be approximated that this part of the plate will have a higher temperature compared to this part, because at T is equal to 0 at the initial point, temperature can be conducted up to this point, not the entire plate. So at that time, if we solve the equation, then it will give a erroneous solution. But in case of discretized solution, what we do is we try to solve the equation for each point of the junction of the grid. So if this is the junction or node of the grid and the grids are equally dimensional, then at each of these points the discretized solution will give a result. So you will not get a single value of T for the temperature of the inside part. Instead, you will get many T's. It will depend upon how much you have discretized the plate, you have divided the plate into. So if you have, suppose, if you are dividing the plate, okay, if you are dividing the plate into 1, 2, 3, 4, 5, 6 unidimensional or 6 equidimensional plates, then discretizing will give you the temperature at these 2 points. As this point, the temperature at this point and this point is already known. This is also known, this is also known, this is also known, this is also known. And also this is also known, this point is also known. These are all known because we know what is the temperature at the edge. We want to know what is the temperature inside the plate. So the discretization will give two distinct solutions of the same partial differential equation at the junction of all the plates. Okay, and we at time t is equal to 0 at the initial time. This temperature can change after a span of time t1, right? And then also you can solve the same partial differential equation for t is equal to t1 and at I plus 1. This is your I plus 1, this is your I, this is your I minus 1. So you want to know the temperature at this point after time t. This is also possible by discretizing, and it will give you a result at this point. But if you just solve the equation, the differential numerical solution method, then it will give just an uniform temperature for the inside of the plate, even after time, spanning of time. Okay. So, however, whatever it is, both differential equation and discretized differential solution and discretized solution are actually the approximation of the solution of that partial differential equation. It is not the true solution. Okay, that is why we try to iterate the solution. In case of discretized solution, we try to iterate towards the minimum error or towards the true solution, where predicted minus actual tends to 0, or in this point, the optimal point, where it will be very nearly equal to 0. So, this approaching of the solution towards the optimal point is known as convergence of the equation. Convergence of the solution. In case of discretized solution, we continuously iterate the partial differential equation and try to find the solution. So, based on the feedback received from this operation, this is the approximate value. What I would say is T approximate minus T actual. We always try to make it 0. And this is what I would say is convergence, moving towards the optimal solution. And it happens when we change. Here there are two independent variables, space and time. If we change this space as well as time and try to minimize it, then we will slowly move towards the true solution. That is the solution which has minimum, very minimum difference with respect to the actual solution. And that is, we also refer as true solution. And when a solution achieves that true solution, it becomes stable. So in case of discretization, there are different conditions that a solution has to achieve to become convergent and to become stable. Right? So today we will discuss about this issue, how to find the convergent and stable solution of the partial differential equation with the help of discretized solution. And always take it in your mind that discretized solution are all approximation. only the solution to the ordinary differential equation will give you the actual solution. But it can give the actual solution with respect to the entire inside space of the metal plate, not at different points of the metal plate. So, if you know the actual solution, then you can approximate it and find the stable solution, right? So this is overall the what we want to discuss today: convergence and stability. What is convergence? When both the independent variable is minimized, approaching towards the convergence, and then when it is indeed minimized, indeed the approximation and actual is very nearly equal to 0, then it is said that two solution is adequate. So what is the condition to be made? Condition to be made is del t must be less than or equal to 1 by 6th of the del x square divided by k. So how k is calculated, that I will come later on. But up to this you can understand that del t is the time variable, which is independent of the temperature T, and del x is the space variable, the x coordinate, which is also independent of time T. Sorry, temperature T. So T is basically a function of T and x. This is time and this is space. This is actually the x coordinate. X coordinate here. So this del x square, this is the condition. Whenever it is satisfied, you can say that solution is stable. That solution is convergent. And what is the stability? Stability is the difference between the actual and predicted. This predicted is same as approximation. Approximated. It is made more accurate to use the term approximation, because here we are approximating the solution. So when it is minimized, the solution becomes stable, and there is also a condition to be met. Lambda must be less than equal to half. And what is your lambda? Lambda is nothing but k del t by del x square is your lambda. What is k? This I will come. So this is the condition of stability, and to get the condition of complete stability, that means no more improvement is possible by the iterations. This will be your condition of complete stability. Here also what is K, I have discussed. Before moving towards the next slide, I have to say that there is two types of solution. One is explicit solution, another one is implicit solution. Now what is the difference between these two solutions? In case of explicit solution, the question is, what is the value of the temperature at the I plus 1 node at what I will say on I plus 1 node at time t is equal to L plus 1. That is the next time scale. Say for example after 3 seconds or 6 seconds or 9 seconds. So when this del t, the difference of time, 2 time, is here 3, and when we are coming to t plus del t, at that time, what is the temperature at I plus 1? Okay, and you know the temperature at I, and also you may know the temperature at I minus 1. So with the help of this temperature, you will find the temperature at I plus 1 after time has spent by del t. because this del t is the time increment and del x is the space increment. Now, as we are trying to predict and approximate something which is outside of the domain of the time for which we have the value or the output value. So that is why as we are moving outside the domain, we are saying it explicit. If instead our question is that what is the value of temperature on I plus 1 at the time t is equal to L, then the solution is become implicit. So remember that in case of explicit, we are trying to find out the output t at I plus 1, but the most important point is after spanning of L plus 1 second. L plus 1 signifies the increment of t, which is equal to del t, and this I plus 1 signifies the increment of x, what is del x. So these changes with the requirement, but this is your solution become explicit as we are trying to find the solution outside of our domain. So if we want to find the solution at the same domain as we are, then it becomes implicit, which is the case of this. We are trying to find the value of temperature at the same node I plus 1. However, at the same time t is equal to L, where where the I minus 1 and I plus 1 are at the same time t is equal to L. But here this is not the case. In case of explicit, here we have to know, yeah, I know the temperature at I plus 1 and I minus 1. I want to know the temperature of I plus 1 after time past del t square. So that becomes explicit as this time domain is outside the domain at which this I plus 1 and I is split. Right? This is the basic difference between explicit and implicit. In case of explicit, we have to find the solution for both t is equal to 0 as well as t is equal to del t or del t anything. But in case of explicit, in implicit equation, this is your explicit, and in case of implicit equation, you have to find the solution, but at t is equal to 0, or at the time at which all the locations are, the heat of all the locations are. So just see the difference of the question and two different types of solutions. So if your question is what is the value of temperature at I plus 1 at time t is equal to L plus 1, it becomes explicit. As the value of heat at I plus 1 and I minus 1 are known, but the value of T is equal to L. But as you are trying to approximate the value of I plus 1 at T is equal to L plus 1, then it becomes outside the domain and the solution becomes explicit. Right? So now how to solve the equation, how to discretize the equation and find the convergent condition and stable condition. So here this is the problem. This is the heat equation which represents the transfer of heat within a say steel plate or rod, right? Steel rod. So this steel rod can be divided into this part. So this is your x1, x2 and x3. And I know the temperature here. I know the temperature here. So I have to know the temperature at here. Right? And say for example, this is your x1, this is your x2, So I have to know what is the temperature at I is equal to x2 and x3. So I already know the temperature at x1 and x4, right? And I want to know the temperature at these 2 points at the same time at which all these points are stable. That means, suppose I apply some heat here, and then after some time the heat will start to flow through the steel rod. So I am saying that when I have applied the heat T to this part of the rod, at that time what is the value of temperature at this point and this point? So this becomes problem of implicit PD or implicit solution, whatever you will say. But whenever I want to know what is the temperature at this point and this point, after time t is equal to t1 or t plus 1, or you can say t plus del t, then it becomes explicit and the solution becomes explicit solution also, right? So just note that this is U, or you can this U is actually the heat or temperature. Xx represent this del square u del x square. X is a space coordinate minus alpha del u del t. T is the time coordinate. Both x and t is independent. So basically, u is a function of x and t. So when these two will be minimized, then you have a probability that you will achieve the true solution. But generally, in case of rod or in case of plate, we compare the approximate solution with the value of temperature that is already known to us. So here you see both T1 and T2 is known. So we try to compare with the approximations, right? So, so I have already discussed about this. What is convergence? When both the independent operators get minimized. So basically, the achievement of true solution is known as convergence. What is stability? Here also you see the error has to be minimized. And the minimum error the method which is stability. Right? So they are always trying to decrease the error towards it. So I have already discussed about the conditions of convergence and stability, right? So there was an unknown term K. So I have said what is K? K is actually the coefficient, and K can be